Hello class. Today we'll be discussing both lectures 11 and 12. Now both lectures 11 and 12 are discussing betas. We've already discussed the different components of the CAPM. A week ago we discussed how to estimate the risk-free rate, how to estimate the market return, and today we're going to finish by thinking about the beta. Now, as I've mentioned before, the beta is in many ways the most difficult to measure because it's unique to each firm. So while the return on the market, right, is the same for all firms in the same country, as is the risk-free rate, the beta actually depends on the risk of that particular company. The standard way to estimate beta is through a regression. So you've seen regressions in your statistics classes before. Essentially what we're thinking about is a simple linear regression. The right-hand side is a y variable, the left-hand side is a y variable, the right-hand side is the x variable. And so in our particular regression, the y variable is the stock returns for your particular firm. Here, for firm J. The x variable, or the right-hand side variable, are the market returns. Now, once you plug this into a regression, you're going to estimate two different pieces. You're going to estimate A, which is the intercept, and you'll be estimating B, which is the slope of the regression. Now, the slope of the regression corresponds to the beta of the stock, and it measures the riskiness of that stock. In addition, when you run a regression, you'll be estimating something called an R-squared. Now, generally, an R-squared is telling you how well your line fits the actual data. So if you think about data that is perfectly linear, you'll have an R-squared of 1, meaning that if you know the x variable, you can guarantee you know what the y variable is. A low R-squared will be where the data is kind of all over the place, and so the line's not really explaining much. Now when you think about this and apply it to finance, the R-squared of the regression then provides an estimate of the proportion of the risk of a firm that can be attributed to market risk. Because the x variable is market risk, if you have a high R-squared, that means that all of the risk, or the majority of the risk, is market risk. The remainder, 1 minus R-squared, is then the firm-specific risk. So a firm that has a very linear relationship with the market, it's essentially going to be a firm that has all market risk. Instead, if you think about a picture where the data is all over the place, and the line doesn't explain much, that's a firm that's mostly firm-specific risk. We're going to move piece by piece and understand how each of the different pieces of the regression are going to tell us something about betas and finance more generally. So to start, we're going to talk about the intercept, the A. Now I have a few different regressions here, or a few different equations. The equation here, this is the regression equation. It's what we were running from the last slide. So A and B then are coefficients from the regression. According to the data, this is our guess for A and for B. The regression up top, this is the CAPM equation. And what we're going to do is we're going to take the B and we're going to multiply it by RM and separately multiply it by minus RF, the risk-free rate. We're then going to move the risk-free rate over and we'll be left with this equation. So it's saying that according to CAPM, the return on any stock J is equal to the risk-free rate times 1 minus beta plus beta times the market return. Now if you compare these two equations, you'll notice that here there's a B in both sides. Here we have an A from the regression and we have a risk-free rate times 1 minus beta from the CAPM. So what is this telling us? It's important to understand that the regression equation is based on data, right? It's what did the stock actually do during this period? The risk-free times 1 minus B, that's based on theory. That's what we thought should happen to the firm according to the CAPM formula. So if A is actually larger than the risk-free rate times 1 minus B, the stock did better than expected during this period. If instead they equal each other, the stock did as well as we expected according to the theory. And if A is less than risk-free rate times 1 minus B, the stock did worse than was expected. The difference between the intercept and the risk-free rate times 1 minus B is known as Jensen's alpha. If it's positive, your stock did better than was expected during the period. Next, when you actually estimate a beta from a regression, you're going to have to decide on several different factors. First, you have to decide on an estimation period. In general, we're going to be thinking about taking data over the previous 5 years. However, in some times, we'll actually limit only to focusing on 2 years. Longer estimation periods provide you more data. That's positive, but the downside is that firms also change, and so shorter periods can focus only on the more recent periods, right, after a change. Second, you have to also decide on a return interval, right, because everything we're doing here is with returns. So we could think about daily returns, so what was the change in price over the past day, over the past week, or over the past month. Shorter intervals are going to give you more observations, right? There's many days in a month or in a week, but they're going to suffer from more noise. And noise is really created by seeing stocks not trading enough. So if your stock doesn't trade that many times in a day, right, then you might actually have a hard time estimating the return interval daily. Third, we need to just understand that returns include dividends. So when you estimate the return, it should be the change in price plus the dividend during that period over the price at the beginning. So it's really important to remember dividends are also there. Finally, we need to choose a market index, and then again, make sure that we include dividends on the index. Next, we need to choose the parameters for Disney. So in our example, we're looking at Disney, we're going to look at 5-year periods, meaning, right, so we're going to look at what was the data, right, the return intervals at a monthly level over the past 5 years. We're going to define the market as the S&P 500. We're going to estimate returns for Disney each month. So for instance, the price for Disney at the end of November was $30.22, and by December it was $32.25. We also found that dividends were 35 cents during that period, so plugging this in, we would find the returns were 7.88% during that month. If we do the same thing for the index, we would find a return of 1.78%. The next thing we need to do is actually run the regression. So let's look at Disney's historical beta. Now, on the X, we have the returns on the market. And the Y variable then is the returns on Disney. And so what we're seeing is, if I know what the returns on the market were in a given month, can I explain what the returns will be in Disney? And if you look at this line, what you notice is that we actually have a fairly linear relationship, right? The line does a fairly decent job of explaining those blue dots. Now, according to the actual information we have, we see that the R squared is 73%. And that actually is in line with what I'm saying, right? 73% of the variation in Disney can be explained with what's just going on in the market. In addition, we find that the alpha is 0.0071, the beta is 1.25, and the standard error, which is in the parentheses, is 0.10. Now, I'm going to expect that each of you are comfortable with how to read regressions and how to run regressions if necessary. So how do we use this information in our class? First, let's look at the intercept. The intercept was 0.712. Now, one way to read this is, if the market is exactly flat, is exactly zero, what do we expect is going on in Disney? According to our estimates, we would assume that Disney's returns is going to be 0.712% that month. In our class, we're going to use this to estimate Jensen's alpha. And there's going to be 3 different steps to estimating Jensen's alpha in general. The first is that we're going to figure out the annualized risk-free rate here, using the T-bill rate of 0.5%, and we're going to divide by 12 to create the monthly risk-free rate. This is going to be a pretty common practice because usually we're going to be thinking about risk-free rates annually, but we're going to be thinking about monthly rates when we actually estimate returns from the regression. The second step is going to be actually estimating the Jensen's alpha. So we're going to take 0.7122% from the regression, and then we're going to say and subtract it off from the risk-free rate at the monthly level, which is 0.042, right, times 1 minus beta at 1 minus 1.252. And that'll give us a Jensen's alpha then of 0.723%. So that's going to be the second step. The third step is we're generally going to re-annualize up the returns. So instead of thinking about monthly returns, we'll be thinking about annual returns. And according to this, the annual excess return of Disney was 9.02%. So that's how much Disney did in excess of what we expected. Next, the beta is actually very simple. We just look at the slope of the regression. So here, we found the beta was 1.25. We also estimated the standard error at 0.10. Now, we're not going to focus on standard errors too much in this class, but there's a very simple rule that we will use. Plus or minus 1 standard error gives us a 67% confidence interval. So knowing that the best point estimate we have is 1.25, we're 67% confidence that the beta is actually between 1.15 and 1.35, which is just plus and minus the standard error of 0.1. We're 95% confident that the numbers are between 1.05 and 1.45. Third, the R-squared was 73%. In our class, this is going to say that 73% of the risk at Disney comes from market sources. 27% then is from firm-specific sources. Now, this is going to be important for our class because we only care about market risk, right? The firm-specific risk is diversifiable, assuming the marginal investor is well diversified, and so they're not going to care about that type of risk. We only have to worry then about the market risk, which according to Disney is 73% of the total risk in the firm. Fourth, we actually use this information to estimate the cost of equity. That's going to be the important thing that we're doing here. So we can take the Disney's beta of 1.25, we can take the risk-free rate of 2.75%, and we can take the risk premium of 5.76%. Now, the risk premium and the risk-free rate were both estimated from previous classes. And if we plug them in, we will find that the expected return for Disney is 9.5%. Now, this is useful both to potential investors and to managers. So first, let's think about this as a potential manager. If we know the expected return of Disney is 9.95%, what that tells us is first, this is the return that we can expect to make in the long term on Disney, assuming the stock is correctly priced and the CAPM is the right model for risk. But it also tells us this is the return we need to make on Disney in the long term to break even on our investment. So for instance, if you're an active investor and your research suggests that there is an investment in Disney that will yield 12.5% a year for the next 5 years, if you also know that the expected return is 9.95%, what would you do? Well, it's easy. You're going to buy the stock, right? Once you actually know that the expected return is 9.95%, if you have additional information that tells you maybe Disney's going to see a better year in the next few years, and they're going to make 12.5% a year on average, then you know that that's a good investment. So we've done all this work to estimate what the cost of equity is, to give us the hurdle rate for equity investors. But once you have that information, what you do with it is actually really simple. Of course, potential investors are, the kind of things we're thinking about in F303. In F303,